To start our study of differential equations, let's get an idea of exactly what it is that we're looking at. So we want to see what is a differential equation along with some basic terms for these. The idea of a differential equation is it's going to be an equation that involves a function and its derivative. And then the solutions of these are going to be functions. So let's look at some examples of differential equations. Here's a differential equation that models the free fall of an object. M is the mass of the object, h is its height above the ground. So d squared h dt squared is the second derivative, which would be its acceleration. G is our gravitation, it's our constant gravity. And so this is our differential equation. And we can use some basic calculus too to solve this. So let's start by dividing both sides by m. I now have the second derivative of h is equal to negative g. And we can integrate both sides. The integral of a derivative just kind of undoes the derivative, so we're down to the first derivative. On the right-hand side, we are taking the derivative with respect to t, so negative gt, plus c, our integration constant. So g is a constant, it works just like a number. The integral of negative 5 would be negative 5t, so the integral of negative g would be negative gt. And then we always need our plus c whenever we integrate. We can now take another integral of both sides. On the left, we now just have h. On the right, for a polynomial, we add one to the exponent and divide. So we have negative g over 2 times t squared. C is a constant, so when we integrate a constant, it would just be that times t. And then we need to add plus d, which will be my second constant of integration. So this is an idea of a differential equation, and this was a very, very basic one to solve it. You can see that my solution here was a function. Integration is going to be very, very important for us. However, they're most of the time much more complicated than this. They're usually very complicated and very difficult to analyze. But these do come up in lots and lots of applications, so we'll actually see a lot of applications as we go. But let's start with looking at a couple of definitions about differential equations. So a differential equation, another way to say it, is it's an equation involving the derivative of one variable with respect to another. So here's another example. d squared y over dx squared plus a times the derivative of y with respect to x plus bx equal to 0. The variable that we're taking the derivative of is known as the dependent variable. In this example, we're taking the derivative of y, so y would be our dependent variable. The variable that we take the derivative with respect to is known as the independent variable. In this example, we're taking the derivative of y with respect to x, so x would be our independent variable. And the values of a and b are known as the coefficients. The next thing we want to look at is the order. The order is the highest order derivatives present in the equation. So if we go back and look at our example, we can see that this particular differential equation has a second derivative and a first derivative. So the order here would be 2, the highest order derivative, which is 2, the second derivative. If we would have had the third derivative, the order would have been 3, etc. The last thing we want to define for now is linear differential equations. So linear differential equations are things where the dependent variable and its derivatives appear in additive combinations of their first powers only. So the first powers part mean I can't have a derivative squared or derivative cubed. The additive part means I can only add or subtract my derivatives. I can't multiply, for instance, y times the derivative of y. I can, however, multiply by the independent variable. So here's the very, very long general form. But the takeaway is we can have as many derivatives as we want. Their coefficients can only depend on x. And the thing on the right-hand side should only depend on x as well. Let's look at some examples. Here's an example of something that's linear. We can see that the coefficient of the first derivative is t cubed, so it's only dealing with the independent variable rather than the dependent. Although technically we should subtract x from both sides, that way the right-hand side only depends on t cubed, and we can see that the coefficients of both the derivative and x are only involved with the independent variable t. This one, the second derivative of y with respect to x plus y cubed equal to 0. is actually not linear, in particular because of this y cubed. I should be able to cube my independent variable, in this case x, my last example, t, but not the dependent variable, y. This one, the second derivative of y with respect to x minus y times the derivative of y equal to cosine x. This one would also not be linear because of this term right here. The coefficients of my derivatives can only depend on my independent variable, x, not my dependent variable, y.